Well, hi there. My name is Ian Paul, and today I'm going to be presenting a Mach-Zehnder Interferometer being used as a temperature sensor. Let's see how it's done. First, my sources. There were 5 papers I ended up consulting. The first one is called The Effect of Temperature and Pressure on the Refractive Index of Some Oxide Glasses. It was published all the way back in 1997. And it's really useful for me for determining some of the relationship between temperature and the fringe spacing that we're going to end up getting out of our interferometer. Just kind of figuring out how materials shrink and grow when they get hot. Then the next paper I was looking at is high temperature sensing using miniaturized fiber inline Mach-Zehnder interferometers. It's a more recent paper from 2010, and it's actually a very miniaturized version of what I was doing, where they are using an air gap instead of a sample. It's kind of funny. You'll see when we get to my design that the materials are reversed. I'll show you what I mean later. But regardless, it was etched into silicone, fully miniaturized, fed by fibers. Really cool. And then the third paper I was looking at is Thermal Effects in Optical Systems by Jameson. It was written in 1981, and I pulled a couple of figures from here. It was useful just kind of in the understanding of the limits of optical glasses. Fourth source there is Fiber Sagnac interferometer temperature sensors. And this is using kind of a really interesting interferometer design. A Sagnac is essentially a loop of optical fiber that you shoot light into both directions of, and then you spin it. And because one of them has to travel further because it's literally fixed a momentum that introduces the interference change. It's a really interesting read. And that's from the year I was born, 1997. And the mechanical and thermal properties of optical glasses. This isn't actually a research paper. It is more of a technical publication. Again, it relates to the density, mostly, of glasses and how that changes as a function of temperature. Okay, of course, Lasers by Siegman, beautiful textbook called the Bible of Optronics. So then Optoelectronics and Photonics by S.O. Casp, a really useful textbook for this. I also am crediting some of my classes. I took Optical Electronic Systems at Oregon State University, and it taught me a lot of what I needed to know to work on this. Wikipedia is a source. If you don't list it, you're probably just a liar. I only really pulled images from there. You'll see them in the next couple of slides. Bing images for a couple of different images when we get down to the interferometers, because you can search by what's publicly available or not. Kind of search by the licensing, which is really nice. And then I got a few pictures from edmondoptics.com. Okay, an overview. So first, I'm going to talk about the background, some things that you might need to know as an aspiring engineering student to fully understand this project. I'm going to talk about my design, and then we're going to go through and do some of the validation. I'm going to go through the Jones matrix of the system, and then talk about, or after really, I talk about kind of how the temperature will affect the path length, and that will affect the phase difference. And then I'm going to just briefly show the results of my simulation. I didn't have as much time as I wanted to make those fully in depth. I was honestly pretty satisfied by the validation, given the scope of this project. And then I'll give you my conclusions and answer the couple of questions I've gotten. Okay, so interference. It may surprise you to learn electromagnetic waves can interfere with one another, right? When they're in the same chunk of space and time, their electrical potentials combine together, right? This can be either constructive, where the two waves, their peaks align and they get big, or it can be destructive, or just kind of flatlines, right? So here you see two waves of pretty much the same exact wavelength, traveling opposite directions of each other, and the red wave there is the resultant interference, right? So waves just combine, essentially. It's a simplified version. So here you're witnessing this happen over time, right? However, it can also be a spatial difference. We'll be using a laser source, which has a very narrow band of frequencies in the light that it emits, right? So because you have just a very little deviation on that wavelength, they won't really be changing due to that. They'll essentially be harmonized And then whatever phase difference we introduce because of the difference in lengths of the legs of our interferometer will be actually showed not across time, but across space. So in optics, we usually see that as an interference pattern. So we'll be seeing little fringes, and we'll be counting those fringes. In this project, I'll end up using a camera, but you could also use a photodetector. So an interferometer. Here we have a Mach-Zehnder interferometer and a Mach-Zehnder interferometer. So the Mach-Zehnder interferometer, it works by sending in a point source. It goes and hits a beam splitter, typically a 50-50 beam splitter. So half the energy goes one direction, half goes the other direction. And they both go and they hit a mirror, right? M1, the top mirror here, is usually at a fixed length. It's not going to move, right? And then, so let's talk about that light. Half the light goes there, it hits mirror one, it comes back, and it goes straight through the beam splitter, right? And it hits the screen. The light that passed through the beam splitter, wave two, it goes and it hits mirror two. And mirror two is a little bit more special. Depending on the type of your interferometer, the mirror might change its angle. It might move forward and back, typically by microns, tiny adjustments. They're actually really high precision machines usually. It's a type of interferometer that LIGO is. And then you have a Mach-Zehnder interferometer, which is what I'll be using here. They're typically used more for temperature sensors. And from my understanding, the light comes in, it hits the beam splitter, hits those two mirrors like you see, hits another beam splitter to recombine. But the phase difference, instead of being introduced by moving mirror two, you put some sort of a change in the index of refraction, like a different material. So what I'll be doing is I'll have air as what light is typically propagating through, and then I'll have a small piece of glass that is actually going to be what we're measuring temperature with. How hot that piece of glass is going to be pretty much the input and output of this system. So what we'll be getting out of this interferometer when we get a difference, because of that glass, it's going to introduce some difference in phase in these two waves, right? They were perfectly aligned, perfectly in phase waves, pretty much the same wavelength when they left the laser source. And then they're going to, have a phase difference introduced. So the waves will be slightly out of phase, but not, fully constructive or destructive. And that's going to produce an interference pattern. So you can see kind of the wave mechanics view of what that looks like up top there, and a more quantized view down below. So thermal coefficients. What happens when glass gets hot? Well, it expands. How can we use that though, right? What's that expansion do for us? Well, really, it means two things. It means that it's going to literally get bigger. There's going to be less distance of the light, like the light will travel less distance before it hits the glass, because the glass got slightly longer, right? So less of its path will be through air and more of it will be through the glass, which is good because that introduces a change in the overall optical length of that leg, which is giving us that phase difference, right? Good. However, when you heat up glass, it also lowers its density. And as I'll talk about in a minute, that can introduce some aberrations and throw off some of our optical system. So not all glass is created equal. There are a lot of types. Like the chemistry behind optical glass is beautiful and ridiculous. Tiny changes, tiny imperfections, impurities make drastic changes. So there's, this is from Jameson, 1981, and really I'm just pulling it here to show you that there are a lot of different types of glass out there. So what we're looking for is some sort of glass that I can essentially minimize, the change in index of refraction while maximizing the change in length. And really what I mean by that is I'm not trying to introduce any aberrations. So I want a glass that is going to have a wider ranging effect right? I want it to grow slowly to measure a larger range of temperature, was kind of part of the scope of my project. Instead, a lot of very precise Mach-Zehnder interferometers are built that have a much narrower range. However, you might, you can get incredibly precise with those materials because they grow more, but you're going to bring your system out of focus faster. So it's kind of a choice of precision there. Okay, my design, let's get to it. So we have a laser source coming in. It goes into a thin lens there. That is then goes right into our beam splitter. It's a 50-50 beam splitter. Goes down, hits those mirrors. The upper path just goes right into another beam splitter and out to the screen. And then the lower mirror, its path has that sample there. So the light's going to come in, get deflected from the beam splitter, hit the mirror, perfectly reflected. It's going to go through that sample, which is going to introduce a phase difference again. Going to reintroduce it's going to come back into the beam splitter. It's going to be recombined, and we'll see the interference pattern on a screen. So we actually have to build this. This is just a Mach-Zehnder interferometer, right? And then we're going to place a sample of the material I chose is borosilicate glass. You might know it as Pyrex. It is most likely the glass that your favorite glassware in the kitchen. It can, as you know, take a pretty good amount of heat as long as it's given to it evenly, because it doesn't expand that much. However, it does expand by a very tiny amount, and enough for me to detect with a laser. So then when we heat it up, it's going to get a little bit longer, and because the light is traveling through that longer than it's traveling, or not, I guess longer than it was traveling through the air after it's heated, the interference pattern is going to change. And that shift in the interference pattern is what we'll be able to mathematically, kind of come back to the temperature with. So we're going to actually measure it with a CCD camera. And then, sorry. Oh my gosh. Sorry, so we're going to measure that with a CCD camera. And then the spacings between the fringes and the fringe width is actually what I'll show you use to regenerate the temperature. So for data collection, we're going to use an Orca 2. It's a nice little digital CCD camera, and I'm actually using this to kind of work backwards for a lot of the specifications of like the wavelengths I'll be targeting, what source I'll be using. So I ended up using a laser that has a 632 nanometer wavelength. So you can see just over from 600. It's pretty much right in the peak of what this camera detects. So that's good for me. And then I'll be using a laser with a 1 millimeter spot size and a 10 times beam expander to bring that out and focus it into the camera. Okay, let's get into the math, the fun part, totally. So beam 1, right? It comes in and it's going to travel an overall distance of D. That's D1 plus D2 plus D3 plus D4, right? And it travels that through air, which has an index of refraction of what I'm going to call 1, right? Beam 2, though, it goes through D1, D3, and then it goes partway through D2 until it gets to that glass, which again, like I've said, its length is a function of temperature. So we're calling that L of T. And then it goes out the glass the rest of the way through its D2 and through the beam splitter out to D4, right? So it travels a distance of D, but travels D minus L of T through the air with the index of refraction of 1. And it travels that L of T, T being, temperature, through the sample, which borosilicate glass has an index of refraction of about 1.5, 168. Okay, so that gives us a total difference in the electrical length that is comes out to be equal to the length of that sample times the index of refraction minus 1. So from that, we can calculate the difference in phase. The difference in phase is a function of the path length, right? Or that changing path length, optical path length there, OPL, that I should probably say, is our good old friend K times the change in path length, and K being equal to 2 pi over lambda, and then L of T, that change in length as a function of temperature, times n-1, n being the negative fraction. And then the phase difference introduced from the fringe spacing comes out to be just k delta x. Once again, pretty much the same thing, but there the fringe spacing is on the screen. So from substitution, we can get back delta x over n times 1 as a function of L of t. And then we're actually going to be using a 10 times beam expander, so we need to take that into account too, because it'll obviously widen the fringe spaces by a factor of 10. So we take our equation for L of t, and then we also have different equation for L of t, right? We have it up there as a function of fringe spacing, but now we have it as a function of thermal expansion. So L0 is the initial length. I'm going to end up using 15 millimeters. And then alpha is a coefficient that's based off the material. It's just an optoelectrical thermal expansion coefficient. Anyway, then delta T is temperature. So from a 15 millimeter sample at room temperature, you have a 20 centigrade, room temperature is 293.15 Kelvin. Alpha for this material is 3.3 times 10 to the negative 6 inverse Kelvin. So that brings us this as an expression for the length of the material. And then we can solve that for the temperature as an expression of that length. And then, so we know that length is a function of that fringe space, we can go through and substitute that in and get a function of temperature as a temperature as a function of fringe spacing. So now we just need to see how big the fringe spaces are. We should be able to work backwards. So let's quickly talk about the Jones matrices. Yay! So Jones matrices and ABCD matrices are actually really cool. They let you skip a lot of complex math by essentially analyzing a phasor version of your system by doing matrix math. So these are some of the identities we'll end up using. They're nice and fun, little matrices. And then something that's important is that with Jones matrices, you actually work backwards. So we're going to be starting with, let's see, do I have a pointer? Heck yeah. So starting over here, right? Leaving the screen, the thing that just happened is we just propagated that distance d4, right? Both waves did that, but we're going to look at the upper path for now. So it just went that distance d4. So that's our first matrix, right? And then it goes through a beam splitter, right? So that gives us our 1 over root 2, 1, negative 1, 1, 1. And then it goes that distance d3. So that gives us 1, d3, 0, 1. It hits a perfect mirror. Here I'm calling it a perfect mirror. You could substitute that in with this if you want a more realistic answer. Right, goes that distance d2, goes through another beam splitter, and then goes d1 and through this thin lens. Okay, so the lower path goes a very similar route. It goes d4, right? Goes through a beam splitter, and then it goes part of that distance through the air, right? And then it goes part of that distance through L of t. So this is the chunk going through the air. Here's the chunk going through L of t, and here is the other side, right? So that all of that is d2 essentially, right here. And then hits that mirror, goes back up, goes d3, goes back to the beam splitter, goes the distance d1, and again goes through our thin lens. So you can run that in reverse, and that's what essentially can tell you, it gives you a phasor. So knowing the frequency range that you were inputting into this system, you should be able to tell the exact phase a wave would be at the output here. Just kind of an interesting analytical technique. So we're also using a 10 times beam expander. So both of these would end up traveling a distance, what I'm calling d5 and d6, and then be expanded in their magnitude 10 times. But that simplifies down to 10, d5 plus d6, 0, 10. Okay, and then my simulation, if you ignore the part of this that just kind of exits reality and goes into the temperatures that are below absolute 0, this is just to show the linear relationship that develops. So in conclusion, that's the design for a Mach-Zehnder interferometer being used as a temperature sensor. Just kind of an overview of it. It's a mathematically validated system. It should work. Verified that it works by doing a little bit of MATLAB. And the temperature range, if you were to ideally thermally isolate that borosilicate, that Pyrex, right, and it wasn't touching anything else. It's a big thing that the Jameson paper focuses on. Is, you know, like lenses getting too big, cracking stuff. So if you can fully isolate that sample of borosilicate, it should be functional from 190 degrees centigrade to 400 degrees centigrade. And it's the overall resolution you would get could potentially be improved by using photodetectors instead of a camera, so you reach a limit with the resolution of the camera. Okay, thank you all. Let me know if you have any questions.